Welcome to my presentation. My name is Mike Wens. I'm the CEO of MinDCet and we do custom power IC. Today I will talk to you about GaN Gate-Driving. First, about the challenges of driving a GaN HEMT. Then about a solution to drive them with a discrete driver that we have developed at MinDCet. The ultimate dream is of course Monolithic GaN IC, which I will also touch. And then finally I will formulate my conclusions. Challenges of driving GaN. It's important to realize that a GaN HEMT is not a MOSFET. The threshold voltage is much lower compared to a MOSFET, and also the maximum gate voltage has to be better controlled in order to maintain reliability. The turn on and turn off times are much faster, so that results in a high DVDT, much higher than compared to MOSFETs. And finally, the capacitance gate source versus drain gate ratio is much lower, which is a risk for parasitic turn-on. All these things combined, they are an ideal recipe for expensive fireworks. And I can tell you that at MinDCet we have done that, so we for sure know what not to do. Anyway, to make your investment in GaN really paying off, you need really to optimize the gate driver and get that right. So here you see a very simple half bridge with some parasitics included. Now, as a designer, you need to take care of these parasitics very well. On PCB level, that means the gate loop inductance. If you don't control that right, you'll get ringing on your gate. And in the end, this will or could destroy the gate or cause false turn-on. The gate resistors need to be very well selected, such a way that you can control the turn-on time and the turn-off time. And also, the pull down needs to be strong enough in order to maintain the GaN HEMT off and to avoid parasitic turn-on. Supply inductance, compared to the inductance of the device itself, is also very important. It will create ringing on the switching node if it's too high. So the decoupling needs to be really close to your GaN power stage. And the same is for your gate driver, of course. On an IC level, there are also some things that need to be taken into account. The dead time control is key. So this is the time between you turn on and turn off the high side and the low side. In turn, of course, the delay matching between those two needs to be very well controlled. We need dead times in the order of nanoseconds for some applications. So that also means that your forward path of your high side and low side gate drive train need to be matched in delay very closely, ideally nanosecond range. Because you have very fast rise and fall times, high DVDT, you need to be immune to that. The high side circuitry of your GaN gate driver will fly up and down with the switching node. And at 100 volt per nanosecond or even more, you really need to make sure that the gate driver doesn't propagate any false pulses or cause unwanted turn on or turn off. Source inductance is inevitably present on your device and also the PCB, and it will create a negative spike on the gate. This has to be taken into account by the driver. It has to be immune to that, and it should avoid to break down, of course, but also to give false triggering. And finally, a problem of gate overcharging exists because of this negative spikes on the source. If you're working with the bootstrap diodes and a bootstrap system, you will get over voltage on the gate if you don't take special measure. So in order to overcome all these, let's say, potential pitfalls, we have developed the MDC 901 at MinDCet, which is a special gate driver, a high performance gate driver. And I really must emphasize that it's a unique gate driver on the market for the following reasons. It's a high low side 200 volt floating true floating gate driver. It has a propagation delay of 30 nanoseconds or less, which is important when you use the system in a closed loop configuration. Any delay in the forward path will, in the end, have an impact on your stability. We have a 1 nanosecond delay matching between high side and low side, which for the 200 volt driver is really very good. And this can be used to optimize the dead time up to a point where the maximum performance can be reached. Slew rate is compatible with 100 volt per nanosecond. I challenge anyone to build a power stage that can switch faster in a reliable way. If you can, there's a good chance that our driver is still compatible with that, but yeah, not so easy to build that. But we are for sure able to take that. So high-speed switching is possible. In order to charge and discharge the gate of your GaN device, you need a high peak source and a high peak sink current. We can deliver up to 10 amps and sink up to 17 amps. Especially also the strong pull down or the strong sink current is important to keep your device off and to avoid parasitic turn on. So again, this leads to a high-speed usability. Up to -4 volt source operation we can withstand, so no false triggering happens or nothing breaks down, which is important because especially during recirculation in the dead time, the GaN has a quite high forward voltage, so -4 volts is possible. Finally, to make a high power dense system, you need to put your gate driver also close to the power stage, which in turn will become hot. So your gate driver will also be heated by the power stage. So our driver can take 125-degree ambient and also can work from -40. The silicon itself is in fact able to work from -55 to 175 degrees C. So this also allows to work at high temperatures, which is an inherent benefit of gallium nitride devices and leads to high power density systems. So all this is packed into a QFN 56 package of 7 by 7 millimeter square. Device features, well, we have a logic 5 volt LDO built in to supply all the internal circuits of the IC, but also a true floating and programmable high side, low side linear regulator. And this linear regulator is programmable between 5 and 6 volts and makes sure that your gate of your GaN really sees that voltage. Regardless if you're using a bootstrap and you get negative spikes on your source, you will never see more than 5 volt or 6 volt depending on what you choose on the gate. So gate overcharge is not a problem anymore. You don't have to fiddle around with Zener diodes or other tricks in order to, let's say, dissipate over voltage. It's regulated and kept under control. Really important to have a reliable system. Another unique feature of our gate driver, the MDC901, is we are able to reach 100% duty cycle because we have an on-chip charge pump. Apart from 100% duty cycle, this also allows for very low and very high duty cycles, which otherwise would not give your bootstrap enough time to charge the bootstrap circuitry. Nevertheless, we also have internal bootstrap diodes that are really very efficient and can work at high frequencies and provide gate power at high switching frequencies if needed. Automatic dead time or programmable dead time is featured. With the automatic dead time, we mean that your gate voltage is sensed, and let's say, for instance, the low side is only turned on when the high side has been sensed on the gate that it's low enough and turned off, then you turn on the low side, and the other way around. Now, this is not the shortest dead time that you can reach. If you really want to have a nanosecond dead time, that's also possible. Then it's a more feed-forward approach, and then we can program the dead time that you want. This allows for maximal flexibility, user ease, and reliability as well. There's an internal temp sensor that allows for system monitoring to monitor the system health. And there's also a undervoltage lockout that avoids insufficient gate overdrive voltage. This is how the block diagram looks like of the MDC901, where you recognize the, let's say, key features in an output stage, the output stages to drive your GaN. And there's a separate source and a sink path that you can then tune with external resistors if needed. There is the level shifters up and down that of course are critical for 200 volt operation and also for the closed automatic dead time. Unique for this driver is also the floating regulators that are truly regulating the voltage that your GaN sees between its Kelvin source and its gate. There is the charge pump allowing 100% duty cycle, the bootstrap diodes that can work together with the charge pump, the 5 volt logic linear regulator allowing for a single input supply voltage. This is how the system looks like real on a PCB. So you see that the power stage, including GaN Gate-Driver, is really compact. For all this functionality, we have one of the most, or let's say the most compact solution in the market. You see that there's only a few external passives needed to accompany the gate driver. This side here is all power stage in an output capacitor and output filter. As you can see at the real life voltage waveform from 48 volt in with 3.3 volt out, we reach fairly good rise and fall times, which can be even faster if you want them to. But using these values, you get no overshoot on the switching node. This is really important for EMI, but also reliability of your system. Efficiencies are easily in the 90%, even with high voltage in versus voltage out ratios. And you see here, in fact, that the high frequency paradigm that is always associated with GaN is not always true. So here we see that the efficiency rises for lower switching frequencies. That is not always true, I have to say. It really depends on your situation, input voltage, output voltage, duty cycle, and some other things like the output inductor. So that changes from situation to situation, but I just want to emphasize that it's not always the highest or the highest frequency that has the best results. So you really need to tune and choose your frequency carefully. So yeah, this is a very nice solution, but looking a bit at the future, what else could we do to improve it even more? And then the ultimate solution is, of course, monolithic GaN IC. So the entire gate drive and power stage in our solution, which is state of the art, by the way, today, measures about 22 by 14 millimeters of board space. Now, a reduction of a factor 8 is possible by putting all this on a monolithic GaN IC. There are some advantages in addition to this miniaturization, which is, of course, a further reduction of the number of components has a positive impact on the reliability of the system. But also your gate loop is virtually non-existing anymore. There is virtually no parasitics anymore because it's on chip, so it's super close to each other. That also improves reliability because there is no overshoot anymore of the gate voltage by any parasitic LC tank that could be ringing. And of course, the overall power density is even more increased, which in turn, of course, puts very high demands on your thermal system. So how do we do that? Well, we use the GaN on SOI technology from IMEC in Belgium, which uses, and you see here a cross section of the wafer. It's a silicon wafer with the glass epitaxial layers again a silicon layer, and then the buffer layer to build the GaN. So this silicon dioxide layer, the glass layer here, in addition with deep trench isolation, allows to create boxes, glass pockets that are able to really physically separate one GaN hem from another in a galvanic way. And this brings a possibility to make true floating half bridges and true floating circuitry. So here you see two implementations that we have made: a symmetrical 32 plus 32 milliohm half bridge and an asymmetrical 32 plus 8 milliohm half bridge. These are 200 volt 10 amp half bridges. The low side and high side gate drive is integrated. The decoupling for the high side and low side is also integrated, which is important to have an energy reservoir very close to your gate. So this is done, and also the bootstrap gap is integrated. Propagation delay is below 10 nanoseconds. Turn on and turn off target is below 1 nanosecond. We also have low side current sensing and temperature sensing. With this kind of solution, there is no concern anymore for the user about gate drive. It's taken care of monolithically on chip. This is the real stuff, so this is how it looks like in real life. So here on the left hand side, we have the symmetrical 32 plus 32 milliohm half bridge with the GaN gate drivers integrated and also the decoupling. Today you see that this implementation is about a 1-to-1 ratio power stage versus gate drive. This is being improved as we speak, so we already did improvements on this design to make that about factor 2/3 smaller, so also a bit faster. Here on the right hand side you see a asymmetrical half bridge where the low side is much bigger than the high side, and this is especially suited for applications where you have a very high ratio between input voltage and output voltage. For instance, 48 volt in, 1 volt out is possible with this kind of ratio. All this has been developed under funded projects and in cooperation with some companies in Belgium, including IMEC for the technology, Thales Alenia Space as an end user, CMAC for high performance substrates, Magwell for electrothermal simulation, and Electa and KU Leuven for the topologies. MinDCet has done the IC design and the layout. So we have mounted this as a chip on board to be able to get maximal flexibility in terms of your signals. So the power is delivered by 125 micron bond wires and the signals through thinner bond wires. Now the chip on board solution is very nice to get flexibility for combining power and signals in a flexible way, and by this allowing to minimize the supply parasitics. But we have to admit that thermally it's acceptable but not ideal. So to get that even better, we are working together with CMAC on a ceramic based module to really get maximal heat performance. This is all very new, so the first measurements are ongoing. We have switching operation. There is decent efficiency, but we need to do some more measurements in the coming weeks and months to learn more. So this is definitely going to be continued. Good. I reached the end of my presentation, so my conclusions are that GaN hems are not inexpensive components, but really have potential in them. So in order to use that potential, it's really key to get your GaN gate driver right. Gate drive, or the proper gate drive, really enables the true benefits of GaN. These benefits are transient speed, so really fast DVDT and almost ideal switching. And this, of course, goes hand in hand with low losses. I presented a state-of-the-art discrete gate driver solution in the form of the MDC 901. And I also talked to you about the future dream that we are bringing into reality, being GaN as monolithic power and monolithically integrated solutions for that. Well, how can we help you? We are based in Leuven, close to Brussels in Belgium. We are a design house, and should you have any interest in this gate driver that we have currently on the market, or for more custom ICs or gate drivers, which we are also able to do, please feel free and don't hesitate to contact us. I thank you for your attention, and I really look forward to answer any questions and to have a nice discussion about this interesting topic. Thank you.